Hello everyone. We are very appreciated to give a presentation on FAST 2025. Our work is ARCR, Adaptive Memory Compression with Page Association Rule Awareness for High-Speed Response of Mobile Devices. Now let us first introduce the background and the motivation of our work. As we know, nowadays people are spending more and more time on mobile devices. The mobile devices include many kinds of equipments, as shown in the left side of the figure, like the smartphones, autonomous vehicles, UAVs, VR or MR devices, robots, and so on. On these devices, a large amount of emerging applications run, like transformer-based AI model, VR or MR services, camera-based services on vehicles and UAVs, mobile games, and short-form videos on smartphones. These applications are memory-intensive, but unfortunately, the memory resources on these mobile devices are scarce. To address this issue, memory compression is widely adopted in mobile devices. However, we find that the page compression is inefficient. This problem negatively affects the user experience. Specifically, we studied the launching speed of popular mobile apps in Google App Store, measured the efficiency of continuous camera shooting, and evaluated the frame rate of short-form videos. Even though the memory space is successfully saved, we can see from the figure that the app launching latency is increased by about 68.7% when enabling memory compression. Also, we can see from the subfigure B that the response time of the continuous camera shooting is prolonged by 1.6 times when the memory is under pressure. Also, we can see from the subfigure C that the frame rate of short-form video playing and scraping reduced from around 50 FPS to about 27 FPS on average. As shown in the right side figure, the software stack of memory compression is in the Linux kernel can block the execution of the main thread. This is also the root cause of the observed user experience degradation. So our further analysis shows that one of the key reasons behind this performance degradation is the sync reclamation mechanism called direct reclaim. Direct reclaim is a fundamental memory reclaim feature in the Linux kernel. It harms the performance because any page allocations must wait for the compression process to finish. As a result, the main task of the foreground app is suspended until its memory demand is met. Even though the kernel thread KSWAPD can compress asyncly, the body system may still get stuck in a loop before enough space is released. We need to know that it is reasonable to compress pages individually, but by doing so, read amplification is eliminated. For example, if we compress 10 pages together, but only access one of them in the future, the OS also needs to decompress all the 10 pages. So we can see it is unreasonable, right? Okay, so in this paper, we show a fundamental question. Can we do large grain compression For example, compress 10 pages in batch, but without increasing read amplification. So this is a fundamental question, and the answer is yes. This is based on an interesting observation. That is, 26.3% of anonymous pages are strongly associated with others. This internal association between pages have not been aware in earlier studies. Like the relationship between bear and diaper, many pages are always accessed together. The association is implicit, but can be mined. If the system is aware of these highly associated pages and does large grain compression on them, the performance has the potential to be significantly improved. And furthermore, the aforementioned user experience issue can be addressed. Now let us introduce our design. In this paper, we propose Archer by association rule mining on anonymous pages. That is, the heap data, the memory compression efficiency can be significantly improved. It is not easy to mine the page association rule in the system layer since many fundamental challenges. I will discuss the challenges later. To tackle the challenges, Archer is designed with 3 normal components, that is FSG, FT-list, and ACR. FSG is a footprint stream generator. FT-list is a frequent pattern tree list structure, and ACR is an adaptive compression region. So now we introduce these 3 key components one by one. The first component is FSG. As we know, traditional association rule mining algorithms like upper and FG groups. This algorithms is useful in mining a static transaction dataset. However, in mobile systems, page access occurs continuously during runtime. Arc should be able to update the page association information as pages are accessed. Motivated by this, Arc collects page access patterns during runtime and generates a footprint stream. And specifically, FSG maintains a sliding window to generate footprint stream and mine the association rules dynamically. The second component is FT-list. As we know, traditional LRU list in the Linux kernel is not suited to support the page association rule mining. So in this work, we co-design LRU with FP tree and propose a new structure called FP list. By co-design LRU with FP tree, the FP list can manage and mine the memory anonymous pages online, and the efficiency is very high. Okay, so the third component is ACR. We should also know that page compression should not be totally abandoned. I mean page size compression. It is also reasonable. This is because there are also many pages have not association, so there should not be batch compressed. Even for the associated pages, the association scale is not a fixed value. For example, page A correlated with three pages, while page B may correlated with 10. Hence, Archer should adaptively compress the pages in practice. To support this feature, this paper further proposes ACR, an adaptive compression region. ACR is implemented based on the original ZRAM region in the Linux kernel. In ACR, pages compressed together are indexed with a virtual handle. Please see the left figure. We have conducted evaluations on real-life mobile devices. So now let us introduce our evaluation results and the benefit on the user experience. Specifically, we conducted our evaluations on 3 platforms, that is Google Pixel 6, Google Pixel 3, and Huawei P20. On these platforms, 3 typical scenarios are evaluated, include app launching speed, photographic performance, and frame rate. As shown in the figure, we can see both cold launching and hot launching speed are improved. Here, hot launching means we launch an app that have been cached in the background, and cold launching means we launch an app that has not been cached in the background. So the launching process is different between these 2 kinds of app launching style. Okay, so we can see the average speed of code launching with Arc increased by about 37.2% on Pixel 3, 30.6% on P20, and 32.9% on Pixel 3. Here, this result is compared to the original compression mechanism in the Android, that is the ZRAM. Okay. Furthermore, the average hot launching speed on the 3 platforms is enhanced by 55.3%, 47%, and 29% respectively. The average photographic speed and frame rate increases by 1.4 times and 1.3 times. Please see the A subfigure A and B. And besides the average performance improvement, more importantly, we also evaluated the tail latency. And from the figure, we can see that the tail latency of the tested scenarios are significantly reduced. And this means the worst case can be effectively avoided. In addition to the above scenarios, we should say that Archer also evaluated the transformer. This is an emerging memory-intensive application. It requires a large amount of memory during inference due to the quadratic scaling of self-attention and high-dimension embeddings. As we evaluated, the average latency of transformer is 7.3 times higher than CNN. However, when enabling Archer, the latency is reduced by 39.2% on Pixel 6. Okay, so in summary, this paper shows that page compression is not suited for memory-intensive applications in mobile scenarios. The key insight of our work is that by mining the page association rule, we proved that large-grain compression is feasible in mobile systems. This issue has not been taken attention in earlier works. And inspired by our observation and to tackle the technical challenges, this paper proposes ARCHER. So ARCHER is an as we know, is an adaptive memory compression with page association rule awareness for high-speed response of mobile devices. Okay, this is our work, and if there are any questions, please don't hesitate to contact us. Okay, so thank you.